So is that okay with you, Paolo, if we start?
Yep.
Yeah.
No, go ahead.
Okay. Well, yeah, thank you everyone for coming. Welcome to this new session of our category seminar. We're very happy to introduce today's speaker, Paolo Perrone, from the University of Oxford, who will be speaking to us about partial evaluations. So the title of his talk is Partial Evaluations, the results so far. So we would like to encourage everyone to make questions at any time during or after the talk. The questions can be asked in Spanish as well. So we'd be happy to translate for Paolo, or Paolo can answer them as well. There will be time for discussion after the talk, and we would like to also encourage any questions or comments during that time. So yeah, please, Paolo, take it away. Thank you very much.
Yeah, thank you. Thanks for having me here. There's some attention to people that speak English, so let me say, eso talk va a ser en español, pero si necesita de una traducción, si algo no está claro, si quiere preguntar en español por alguna razón, está bien, puede preguntar, pero por favor despacio, que no estoy acostumbrado a hablar de matemática en español, ¿vale? Okay, so I'm going to talk about partial evaluations, and let's jump right in. Let me just say this is joint work with a bunch of people that I've put here. So I'm going to talk about some of the things we have figured out with, well, a subset. So these people on the Applied Category Theory School of 2019. The paper is in the abstract, and some more modern work that I've been doing with Walter Tholen. Okay, so what's the partial evaluation? Okay, so maybe let me ask, I don't know how the audience is. Is everybody familiar with monads?
Yeah, I think you can assume everyone's familiar with monads.
Very good. Okay, so let's stay for now in the category of set and take a monad on set. Take also a T-algebra. So Eilenberg algebra. So you probably know that algebra sometimes are somehow spaces which are closed under the operations encoded by the monad, like especially if the monad comes from Elsevier theory. So as an example, let's say that T is the free commutative monoid monad. And an example of an algebra could be natural numbers, with addition. That's the monoid, okay? So how the map TA to A goes. So the thing is, TA can be seen as the place whose elements are like not just numbers, but formal expressions, formal sums of numbers. Say, that's an element in here. And then the evaluation, the algebra structure map just does this sum. So 3 plus 4, 7, plus 5, 12, plus 6, 18. Okay? So the important thing is that this sum is purely formal. Okay? So this is not equal to 8. The result, 18. The result is 18. Okay? Okay, great. So that's an evaluation of the sum. So this is like an evaluation. Now, can we also say that this formal expression above can be evaluated to the formal expression below, but not completely, partially. So this is a partial evaluation. How can we describe this? Well, how can we describe this using category theory in terms of monads? So the most natural way to do this is the following. Okay, what does it mean that we have grouped these guys? So let's go a little bit up in the structure that the monad has. So up here, we can have TTA. Maybe let me go further to the left. I need some space. And now there are two maps. They go from TTA to A. We can, first of all, apply T to this map. But we can also apply the multiplication of the monad. This guy, this component at A. What do these maps do? Well, let's go here maybe. So in TTA, what are the elements of TTA? These are formal expressions, informal expressions, right? So formal expressions whose terms are themselves elements of TA. So they look, for example, like this. So there's a sum between these things. And the blocks, the boxes, are telling that you can't sum the stuff in here with the stuff in here. Because those are, this thing alone is an element of TA, okay? So this plus is in TA and this plus is in TTA, okay? All right, so these are the boxes. And now, what do these maps do? So mu and TE do different things. So TE is the easiest one because T, well, it's a functor image. So T says applies E to each term in the formal expression. So basically evaluate the blocks. So that's like 3 plus 7 plus 11. Mu takes this nested formal expressions and flattens it or denests it. So basically it removes the boxes. Okay. Let me also say this has nothing to do with how the theory is presented. Of course, at this level, you can remove all parentheses because it's associative. I'm not talking about that. This is about formal and not formal. Okay, and you can probably see that then the thing on the left is a partial evaluation. I mean, sorry, can be partially evaluated to the thing on the right. So how do we do it in our case here? Well, here in TTA, we take so you see now, let me make some space, that applying mu, we get this, and applying TE, we get this. Okay? So definition, given elements of TA, a partial evaluation from P to Q is an element phi in TTA such that, well, as we have said there, mu of phi is B and TE of phi is Q. Okay? All right. You can do this outside the category sets. Of course, you don't have elements, but you can have like arrows into your object, and so you can view them as variable elements. You can do exactly the same. But for now, let's stay in set. Okay? So let's say some basic properties of partial evaluations. So these are a bit of a consistency check. First of all, doing nothing is a partial evaluation. Why? Well, for this reason. So take TA. So in the case of natural number, take, I don't know, 3 plus 4. That's an element of TA. Then you can apply T eta in here. So that T eta. So what does eta do? Adds a box for each term. Okay. And now what we can do is either apply mu or apply TE. And you see that applying mu, remove the boxes, and applying TE evaluates the boxes, but there's not that much to evaluate. Okay, so these are the same. Why? Well, you may recognize this is the left unitality, no, the right unitality of the monad. And this is T applied to the unitality of the algebra. Okay, so not just in the example on the right is always commute. So it's like some kind of reflexivity or identity. And another thing that we can do, totally evaluating, is a partial evaluation. Why? Well, that's a little bit more involved, but not that much. So what is total evaluation? So you have TA, you evaluate it, and then consider it again as a formal expression. So that's like 7, and then 7, but as a formal expression. What's the partial evaluation that witnesses this? Well, here what's going on. So we have, maybe let me draw these arrows slightly differently. Let me do it this way. Now, eta is natural. And so this diagram commutes. Okay. But now, so that would mean eta adds a little, a big box here. And then evaluating the boxes, we get 7, okay? And now here we can apply mu, which removes the boxes. That's the same. Okay. So again, this is naturality of eta, and this is the other unitality, so that left unitality of the monad. Okay. So total evaluations are partial evaluations. Doing nothing is a partial evaluation. If you want, partial evaluations are all that happens in between. Between evaluating totally and doing nothing. Okay. Very good. Let's see some examples. I mean, some further examples besides summing numbers. So let M be a monoid. I hope I don't have to convince you that this thing is a monad with unit of multiplication given by the ones of M. Usually, this is famous for groups, and you probably know that algebras are sets with a monoid action. You can do this in every monoid category, not just in set. You can do it with Lie groups and whatever you want. So these are like the usual group action or like monoid action on a set. Okay. What is a partial evaluation? So partial evaluations are between things in here. Let's try to see what they are. So there's a partial evaluation from mx to, let's say, ny. Well, if and only if there's something in m times x. So some kind of like a, b, z, such that now this multiplies a times b. So a plus b, let's say plus, is equal to m. Okay. And here we have to TE. So that's applying the action. So that means that b z is y. Okay. So necessarily z has to be equal to x. And m has to be equal to a. Sorry, that's wrong. A has to be equal to n. All right. What does this mean? This is what it means. Suppose that, for example, we are on real numbers and translations, okay? What is mx? That's like a formal translation. That's like we are in x, we are here, and we have this amount of gasoline in our tank. Now, if you go all the way to 0 m translating x, then you have used all the gas. A partial evaluation uses the gas partially. So m is the sum of this amount of gas and this amount of gas. And we always, if we only use this part, the other part is still in our tank. Okay? Now, of course, for groups, this is trivial because you just get anywhere in the orbit. You can always, like a gas is reversible in groups. But for monoids, at least for those monoids which are not groups, then this tends to be directed. And so this is interesting, okay? So this is like use part of the gas. Okay, I'm gonna give 2 more examples later in the talk. If you want to see even more examples, just let me know, because partial evaluations are everywhere. So for those of you that are into homological algebra, for the case that M is a group, this gives a thing called the bar resolution. So you may see the link, but I'm going to tell you a little bit more about that in a moment, okay? So one of the main questions that we had when we discovered this thing is, can we compose partial evaluations? So here's, again, the case of natural numbers and addition, okay? I have this formal sum. I can partially evaluate this to, say, 2 plus 2 plus 1, right? What is the witness? Well, take 1 plus 1 plus 1 plus 1 plus 1. So you see that this does a job. Okay, I can also partially evaluate this thing to 4 plus 1. How? Well, let's say like this. Right? So here, mu will do this, and TE will do this. Okay, great. Can I go from here all the way to here in one step? Okay, let's see. I mean, you can probably just go by trial and error, but let's try to find the principle, because I don't want just to solve this example. I want to do this in general. How, okay, take this here. How did we obtain this 2? This 2 was 1 plus 1. This 2 was coming from here. Okay, so let's replace. Let's replace it by, so instead of 2, now we have the square that gave us that 2. We have replaced these 2, seeing what this arrow did to that. Same for the other one. Do I fit? Sorry, need a little bit more space. Okay. Does this work? Well, not quite. Because this square corresponds to this box. And so this, we need a separate box here. Okay.
Paolo, I'm sorry. There's a question by Carlos.
Yes,
so,
please.
So he's asking what is the difference of partial evaluation with an operad, with structure and the monoid?
I mean, I suppose one could define this for operads too. But so this is very much linked to operad. Operads are the nicest case, so I'm about to tell you now. So let's see, if in the next 5 minutes you think your question hasn't been answered, please ask me again. Okay. But that's an excellent question, because the substitution thing has a lot to do with operads. So, okay. Now that does not yet give us a partial evaluation, right? However, we can now remove the inner brackets, somehow glue along these inner boxes, which appear both here and here, right? So glue along them, and we're left with and you see this one now is such that if you remove the outer brackets, you get the first expression, and if you evaluate them, you get a second expression. What is this map that we applied here? Well, let's remove the brackets for each box. And you also see that here, you can just remove the brackets, the outer ones, and here, this is evaluate the inside of the inside. Okay, so where are these elements? We are here. This is in TTA, sorry, TTTA. This is in TTA. This is in TTA. What is going on? Okay. What happens here? So it turns out that, as we said, the algebra of a monad was just the tip of the iceberg of something more interesting, which is partial evaluations, of which E is the equalizer. And here, TTA. And we have the trivial partial evaluation given by T eta, if you remember, like the identity. There's more to that. So this is again just the tip of the iceberg, because there's TTTA. And here we have these 3 maps that we have on the left, which are like mu, T mu, TTE. And of course, here we would have T eta and TT eta. And we could keep going. So there's an entire simplicial set. Called the bar construction. Some of you may have heard, as I said before, bar resolution. So you probably know that if you're like in suitably abelian nice categories, then simplicial sets are basically the same as chain complexes. So this simplicial set becomes a chain complex, which is usually called the bar resolution. In particular, when the monad in question is this group action thing. So you can view this bar construction as a very wide generalization of the bar resolution. So you can't quite do homological algebra here, or at least I'm not able to. But you can do some homomorphism theory. And this is going to be important. So here, okay, that's an augmentation, so forget about this part, okay? These are like points, so 0 simplices, formal expressions. These are 1 simplices, partial evaluations. These are like 2 simplices, or triangles. Let's maybe try to see the geometry of what's going on in here. So vertices of a triangle are formal expressions. This can be evaluated partially to this via, how do I do it? Via this thing. 1 plus 1 plus 1 plus 1 plus 1. So that's the arrow, okay? And mu and TE are source and targets of this thing. Just as well, this can be partially evaluated to 4 plus 1 via 2 plus 2 plus 1.
I'm sorry, Paolo, there's a comment in the chat,
Yes.
in the YouTube channel by Omar. So he's saying that it's not just about construction in the homological algebra case. It seems like in general, partial evaluations are 1 simplices in a simplicial object, isn't it?
Yes, that's exactly what I'm about to say. But yes, that's exactly what it is. It's an excellent point.
So
that
this is the
kind of sounds like I want to say that what I'm going to say is an excellent point. I don't mean to have that much of an ego, but yeah, it's a great comment. So you're right on track. So yeah, partial evaluations are 1 simplices in the bar construction. And if we have 2 composable partial evaluations, then their composition, the witness of their composition will sit in the triangle, will sit in here. And it was this thing, this nested thing that we had. And now removing, so applying the third map, the boundary, like the face map of this thing, then we get the composite partial evaluation. Okay, so in this sense, witnesses of compositions are triangles. Kind of, so to say, tell you that this triangle commutes in some sense, like a homotopy between these 2 edges, so to say. Okay, so the right word, the rigorous word, is canfiller of this inner 2 horn. So a horn is basically a shape like this in a simplicial set. And a filler means that the whole triangle is there. And they can, of course, then apply the face map to get the missing edge. And that's kind of like composition. Okay, so now the question is, when do these exist? Not always. There are counterexamples. Counterexamples are a little bit involved, so I don't think it's very helpful to do one real time, but you can look in the paper, in the one partial evaluations of the compositional structure of bar construction, I believe section 3, and it's all spelled out. Okay, but so the important thing is that they do not always exist, but in nice cases they do. So let's see, let's go up here. So let's maybe rewrite this part of the diagram. So we were having TI, 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 TTI, 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 and then we had TE, TE, T mu, and let me now do the other maps in yellow. Mu, T, TE, TE, and mu. Okay, so what was happening above? We had something in here, which was a partial evaluation from here to here, and something in here, which was the partial evaluation from here to here, such that they agreed down here, right? Like the target of the partial evaluation was the source of the next partial evaluation. And we're saying we want something in here that closes the diagram. Well, you know that the thing above here exists if we have a pullback, right? Okay, so what is the square? If you can see, this is a naturality square for mu. Okay. Now recall, mu is called a Cartesian natural transformation if its naturality squares are pullbacks. Okay. Now, since we're not interested in the uniqueness of the thing in here, but we just need something to exist. If there's still, it's not so bad, right? We can still compose our things. Well, then we are interested also in the weaker version. So mu is a weakly Cartesian natural transformation. If its natural square are weak pullbacks. What is a weak pullback? Is a pullback where the universal property has just existence and not uniqueness. Meaning that if you have any object here and a pair of maps down here that make the whole thing commute, then the map here exists, but is not required to be unique. Okay? I don't know how to do it. Like this. I mean, it's fine if it's unique, but it doesn't have to be. Okay? I don't know what's a symbol, but okay, that's a weak pullback. Okay? And let's give an additional definition. So a monad is called Cartesian if mu and eta are Cartesian and T preserves pullbacks. The monad is called weakly Cartesian. These are definitions. Huh? Well, if mu, eta are weakly Cartesian, and T preserves weak pullbacks. And the monad is called Bach-Chevalier, or BC. Well, let me say, if it's the same as above, except the unit. So if mu is weakly Cartesian, and T preserves weak pullbacks. Okay, why are we interested in these? Because of the compositional structure. So, well-known fact, the bar construction, so the simplicial set of a Cartesian monad is the nerve of a category. So composition unique, and it's also associative, it's unital and everything. Okay, maybe why? Well, intuitively, the thing is, if you have many partial evaluations, have like sorry, it takes a while to write. So suppose you have, in this case, 4 partial evaluations which are composable, okay? Well, then this thing is a pullback. So there's a composite here. This too. And this too. My handwriting is going worse and worse as I keep writing. Okay, so what does that mean? So these were 4 partial evaluations, right? These are things that looks like this. Now we're saying that here there's a composite, here there's a composite, and here there's a composite. But now, here, this is again a pullback. Let me say T4A. And this too. So this is again a pullback. Sorry, mu is not here. Mu is here. And again, T, 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 E. So what does that mean? That means that basically that the composite of this and the composite of this and these are the same composite. It's just one. That's associativity. There's a unique thing up here. And here too. And there's also a unique thing up here. So basically, any tuple of composable partial evaluation will have a unique composite. Okay, you have seen this before. So example, M times something is Cartesian as a monad. And you probably know that, at least in the case of groups like that, the bar resolution gives indeed a category. Like, and that's something like a bundle of orbits in some sense. Okay, so it's not the action category, yeah, because for algebras, so the action category has this as set of objects, while we have this as set of objects, formal expressions, but it's related. Okay, and other example is the free monad is Cartesian too. Okay, where you don't. Okay, so great. So do weakly Cartesian monads give quasi-category then? Like some higher version with less ambiguity? Well, we thought so, but no. So first we found a counterexample, and again, it's a little bit involved, so you can find it in the paper, I believe, again in section 3. But Cartesian monads give categories. Weakly Cartesian monads do not give quasi-categories. They give some other things. So in the paper, especially thanks to Brandon Shapiro, we have given a lot of conditions on the monad for example, when partial evaluation compose in which way, and also for other questions, which I don't have time to talk about today. Like, for example, when partial evaluations are invertible. So when do these things from things that look like groupoids? You have also all those questions, okay? So they're all in the paper. Let me just say what we found for composition. So we find that if the monad is BC, so I mean, we already know that if the monad is Cartesian, then we have a category. If the monad is BC, well, then only inner spans have a filler. So by which you mean that the simplicial set has this property. So the simplicial set has this property that it's not quite count filler. Just in dimension 2 looks like a count filler, and that's why we're thinking it was something with composition. It is, but then the next ones are not associativity and the like. So we have like di dj x of n minus 1. So these are the face maps, the dual to the face map. J minus 1 with they have to differ by at least 2 because they have to be inner. So that's like I is less than j minus 1. Okay. So example, this thing here, because this thing is like d0, this thing is like d2. This would be d1, but we don't care about this one. Okay. So this square has a filler. Okay. They differ at least by 2, so they're inner. Things like this are weak pullback. If we have weakly Cartesian, so remember weakly Cartesian is like BC, but there's also eta. So we have something about unitality here that's nice. So we have similar conditions here involving also the degeneracy map. So let me see if I can be lazy. Yeah. So here we have the degeneracy maps. And so this is n plus 1 and this is n. Is this correct? I believe this is correct. And the one here would have to be the other one. So Sj, Sj, and here we have di plus 1. Yeah. These two are weak pullbacks. And that one too. Okay, because the weakly Cartesian is stronger than BC. This is something that we call inner complete. And here's something, I can't get into the details, but here's an interesting thing. Inner completes include categories. However, the following happens. So if these are inner completes sets, and these are quasi-category, if something is both, then it's necessarily a category. Okay? So crucially, weakly Cartesian monads, such as, for example, the free commutative monad, are not quasi-categories, because if they were, they would be categories. So it's somehow an orthogonal generalization to the direction of quasi-category. It's weaker in a different sense. Okay? So if you're interested more in this, please look at the paper. We have a lot of other conditions. For example, I repeat, when things look like groupoids, so when partial evaluations can go back, you can probably imagine that group actions can go back, monoid actions cannot in general, and so on. Okay? So it's all worked out very nicely. And yeah, please take a look there. Okay? So in the last time that remains, I want to give two notable examples of partial evaluations which took even separate papers to work out because they're really non-trivial. Okay? And maybe they can showcase how powerful the concept of partial evaluations could be. So the first one is for probability monads. So partial expectations. So partial evaluations for probability monads are conditional expectations. So I worked this out for one particular probability monad, which is the Kantorovich monad in the category of metric spaces, because it's a very nicely behaved category for the purposes of what I wanted to do. You probably know that measure theory is full of technicalities that one has to take into account if one wants to do things right with conditioning and so on. So Kantorovich monad is a monad that works well. I can give you more details about how it works. Let me just tell you that it's in the category of complete metric spaces, and algebras of these monads are complete metric spaces which are like convex, are closed under centers of mass. So the idea is algebras, you have a probability measure here, and you get something like a center of mass, like, you know, something like this. Okay, so that means if this is your space and you have a measure, then you look where the mass is mostly concentrated, like the barycenter. Okay, that's the result of that. That's the average. Okay, so what are partial evaluation or conditional expectation? Like as in the one that's used to form conditional probability rigorously. The actual statement.
I'm sorry, Paolo. There's another question.
Yes.
Yes, so this is from Omar again from the YouTube channel. So he's asking, well, so he's saying that the simplicial sets for weakly Cartesian monads do have fillers for spine inclusions at least.
Sorry, could you repeat again?
So the simplicial sets for weakly Cartesian monads, do they have fillers for spine inclusions?
Spine inclusions.
So yeah, maybe.
I believe so, but I would have to look at the paper again.
Okay.
Oh, by the way, let me answer the previous question. So Cartesian, so all the monads that are presented by an operad are in here. So if you do, so to say, partial evaluations for operads in such a way that the concept is the same as the one you would get with a monad that's related to that, then you're in this setting. It's the nicest possible setting, and they compose as in a category.
Okay, yeah, thank you.
Okay, so where was I? Oh yeah. So what's the actual statement here? The statement here is that let these be f and g be random variables on A, random elements of A. A is an algebra, like a, say, a Banach space, for example, real numbers. So this is a measure space, and this is another measure space. Okay. Then if there exists a measure preserving map from omega to omega prime, so this is the situation. Now this diagram does not commute, huh? And G is the conditional expectation of f given h. So a measurable map here plays the role of a coarser sigma algebra. Then there exists a partial evaluation for the probability monad between the measure f star mu and g star mu prime. So we have two measures on, say, R. Partial evaluation means that it's like a not necessarily all in a center of mass. That's a total evaluation, but it's like a more concentrated measure. Okay. There's already a notion of more concentrated in probability called second order stochastic dominance, or like conditional expectation. So what I want to say is that these things are the same. And moreover, there's kind of a converse, like it's somehow weaker, and like if P and Q in PA have a partial evaluation, then there exist random variables such that G is a conditional expectation of F given something. Okay, so moreover, all partial evaluations arise that way. And so in some sense, partial evaluations are conditional expectations, meaning that they are what's left of conditional expectation when you look at the image measures of your random variables. Okay. So you see, this is not that obvious. I mean, it has to be like this in the sense that we had already a notion of partial thing in probability, but it's nice that it gives a known concept. It's one of the nice things about category theory is that you get things you knew already in a new light. And another non-trivial example of partial evaluation. Okay, so again, there's an entire paper about it, all my work with tolerance. So let me just say one of the statements in the paper is that kind of like here, partial colimits are kind extensions, are pointwise, the nice kind, left kind extension. I mean left because colimits. By which I mean what? Okay. Say cat, the category of locally small categories, possibly large. Okay. There is a monad P from cat to cat, which is called sometimes a small free co-completion or free co-completion, which takes the category and gives the full subcategory of the category of free sheaves, which are small colimits of representables. Okay, so you probably know that the unit embedding is something like a free co-completion, but you can't get a monad out of that because of size issues. But then usually you don't want large colimits anyway. You just want small colimits. So you just want to take the small. So not all pre-sheaves, so some of them are too much. So just the ones that are, you just take the free completion of the limits that you would actually want to take in the first place. This gives a monad. I mean, of course, it's a two monad. But like it's not a relative monad. It's really a real monad, just higher dimensional. Okay, and algebras are co-complete categories. I mean, small co-complete, so all small colimits, and the categories can be large, but locally small categories may be large. Okay, so not just posets. With a choice of colimit. How do the structure maps look? It's like a coend. You take a pre-sheaf and you get this thing. It's a weighted colimit. So this is the copower or tensor, not the one of monoidal categories. Let's see. Okay. Exercise proof this exists, even if C is large. The thing is P is small. Okay. Now, I would like to tell you, okay, look how much this thing looks like this. So I would like to say that the monad of small pre-sheaves is a Giri monad in disguise. And that's why people use coends, like people write coends as integrals, because it's basically the same. I mean, it's not the same, obviously. They're different concepts, but they work in ways that are extremely similar. Okay? Okay, and now what I want to say is that what for probability monads are conditional expectations, for the free co-completion monad, these are kind extensions. So let's get a statement, which is So let P and Q in PC, small presheaves on C, where C is co-complete, like an algebra. Okay, the following are equivalents. First, there is a partial evaluation. I mean, of course, here we're in two-dimensional world, so up to isomorphism from P to Q for the monad P. 2. Now, there exist small diagrams.
I'm sorry, Paolo. I think there's a comment again in the YouTube channel, and
Yes,
it might
okay.
be anticipating what you're going to say. But so this is Biomata. So
Okay.
he's saying that partial colimits being left can extensions sounds like the classical fact that left can extensions along and not vibration is given by taking colimits of the fibers.
Yeah, let me say yes. That's the easy case. What I'm about to say is slightly different, and I would say better in some sense. Of course, depending on everybody's taste. But I think so. These are all left kind of extensions. Let me.
Okay.
It says that there exist small diagrams. I, D to C, and J, E to C, and the functor F here, not an up vibration, any functor. Now, such that, first of all, I mean, how are D and E linked to PC? Well, D, so let me say, P is the, let me say like this, the D colimit of representable. So that's the equivalent of the image measure in probability. So what I mean is P is not the colimit of D, but the colimit of shape D of representables. So after the unit embedding. Okay, so if you want, P is a colimit of this, this functor here. Unit embedding. Okay. So it's something like the weights that would give you the colimit, pretty much like the image measure of random variable, but for weight colimits. Well, Q is the E colimit of representables. Okay. So P and Q are like this, the things given by D and E. And 3, E is the pointwise left can extension of D along F. In other words, Q is a partial colimit of P if and only if Q arises from a diagram, like it's a free colimit of a diagram, which is a left can extension of a diagram from which P arises. Okay, so you see, this is again this diagram here does not commute. Okay, it's just that the resultant thing will have the same colimits. And if you wanted something like a best approximation, in some sense, to a commutative diagram that we can have in case F is not an equivalence. Just as well, in the case of conditional expectation, this does not commute. And again, instead of the same colimit here, they will have the same center of mass. But again, it's a best approximation to commuting that we can have here in case H is not an equivalence of measurable spaces. So in some sense, like coends are two integrals as left-hand extensions are to conditional expectation. So things like this that not necessarily commute. You try to make this commute as much as you can. It doesn't. What's the best you can do? And okay, here's how I conclude. So I don't think there's any other way of expressing this without using partial evaluation. So I think this is a very nice case that shows how partial evaluations are an important categorical concept. Like before, like just partial sums. Okay, I guess maybe somebody could use them in, like, for computation purposes, but they probably have already better tools for that. I'm pretty sure they do. On the other hand, as a categorical concept, what are categorical concepts good for usually? To unify things, to show that some patterns derive in different settings. And here, partial evaluations as a categorical concept serve the purpose of showing that left-hand extensions and conditional expectations are extremely analogous. And the way to make it precise was precisely this concept. So the intuition would have suggested that these diagrams almost commute. How do you make this precise? Well, here it's how you make it precise. And so these were like the two non-trivial examples of partial evaluations. Okay, I think I will stop here. I'm happy to take any more questions if you have them.
Thank you very much for the great talk, Paolo. Those were really nice final results. Great. Yeah, are there any questions or comments for Paolo? Yeah, Bob has a question. Yeah, please.
Yeah, should I put my, please?
So suppose that you have some, let's say, algorithm for calculating the square root of 2. So you calculate it and you get 1.12 and so on. So 1.12, would that sort of thing fit into your partial evaluation?
Good question. That's a good question. Like do approximations, give an example.
Yes.
So, all right, here's what I can say. So the short answer, I don't know, but a slightly longer answer, here's how I would go about it. So I know that Walter Tholen has this book, Monadal Topology,
Oh, yes.
where he shows that limits of ultrafilters can be seen as lax algebras of certain monads, where the structure map, I mean, modulo taking some suprema and so on, gives like the limit where the ultrafilter should converge. I believe that partial evaluations there would give partial convergences to the limit.
Yeah.
And partial evaluations are also defined for lax algebras. It's pretty much the same idea, but there are some more errors in there. So that's how I would try, but I haven't checked, so maybe that gives something completely different.
Okay, thank you.
Nice question, though. That's a good thing to try to check.
Thank you, Paul. Are there any other questions or comments?
There may be some questions on YouTube because there's a little bit of lag usually.
Yeah, well, most of the questions I think were already answered
Okay.
by yourself in the YouTube channel. But yeah, hopefully.
Mm-hmm. Okay, let me stop sharing in case I can share again in case anybody asks.
Yeah, so Omar says he already asked all the questions that he wanted to ask, but he also wanted to thank you for the talk.
Oh, very good. Yeah,
Yeah.
thanks for the questions. They were all of them on point.
Yeah, I suppose well, you mentioned the statement for, so what are partial evaluations in the Kantorovich monad? So I suppose you have so for other probability monads, you have some sort of similar, very on point, results. Yeah, where can I get, well, in the papers, I guess, I can look for them.
Yeah, so if you want to see, there's this paper that's called Monads, Partial Evaluations, and Martingales. So let me see if I can find it so that I can give the exact reference. Monads, Partial Evaluations, and Rewriting, I'm sorry.
Okay.
So for those, let me share my screen again shortly so that people can. It's this paper here on the archive.
Okay.
So here, there's section 6, where we talk about partial evaluations and probability.
Okay.
And there we work out the case of the distribution monad, which is like the one of finite convex combinations.
Yeah.
So instead of integrals, we have sums. So pretty much the same thing that goes on in the infinite case is already happening here.
Okay.
Like, the only difference is like measure theory, but like conceptually, things are pretty much the same. So if you want to see what happens in the easiest case, it's like a prototype, then it's here.
Okay. Thank you. Yeah, what are directions where this is going?
Yeah, so depends a little bit.
Okay.
On the side of partial colimits,
yep,
I would love to do the same thing for enriched category theory.
Okay.
If it's possible. And I have to do weighted colimits, and of course they're the same in the non-enriched case, but then things may be a little bit different in the enriched case. But the monad is there, like it was defined, I think, by Steve Lack, anyway, by the Australian school. So the only thing that has to be done is like to work out what the partial evaluations are.
Yeah.
And on the probability side, there's a lot to be done because like conditionals are notoriously tricky.
Yeah.
In probability, especially if you want to look at them from the categorical perspective.
Yeah.
And so there's quite some work there, and that we have to do, and try to understand better what's going on here and see where partial evaluations actually fit. But a nice thing that this gives is that, so like a chain of composable conditional expectations.
Yeah.
Like if you have a stochastic process, such as pairwise any two random variables and the duration of conditional expectation, that's the same thing as a martingale. I mean, the martingale is usually that, but reverse. But,
yeah.
Okay, up to reversing of the arrows, which as category theorists, we are happy to do. That thing is a martingale. And I would really like to see if we can talk about, for example, convergence of martingales and things like that, like theorems of probability theory, really just using the theory of partial evaluations. And we have some partial results in some sense, in this sense, but yeah, there's still some work to be done there.
Okay. How does this relate to the framework of with Markov categories?
Yeah, it does. I mean, of course, for the case of probability. So yes, so this idea of partial center of mass and of like conditional expectation
Yeah.
is in statistics and in mathematical finance is called second order stochastic dominance. So we have this paper together with Tobias Fritz, Thomas Gonda, and Eigil Reschel that so where we finally linked Markov categories with probability monads.
Yeah.
So and show the relationship between the two concepts. So very often the Kleisli category of a probability monad gives a nice Markov category.
Yeah.
I mean, of course, sometimes there's some compatibilities that have to be done. But for example, for standard Borel spaces like Polish spaces, so to say, this works and works very nicely. And so you can translate the concept of partial evaluation from the monad to the Markov category. And it's actually rather elegant if you allow for chrysomorphism. So the partial evaluations become a little bit different. They get like other arrows, but they can be perfectly translated. And so that way you can talk about stochastic dominance, so basically of partial evaluations, in any nicely enough Markov category. Which was pretty nice because then this was allowed, well, mostly Tomasz Gonda did this, translate some results in statistics that have to do with stochastic dominance into the language of Markov categories and even prove them just using string diagrams generally. So it was, I would say that was pretty nice, and I was very happy when he came up with all these ideas.
Where is this? Which paper is this?
Yeah, let me maybe say this too. So let me share my screen again. It's this one. It's this paper here. So a representable Markov category is just a name we invented, which is just to say a Markov category which is the Kleisli category of a probability monad on the subcategory of deterministic monads. And so in there, where is that? Here, second order stochastic dominance. That's the same thing as partial evaluations, except that here is how partial evaluations look in the Markov categories. That's equation 4.6. So instead of mu and PE, we have sampling and E, where sampling takes a probability measure and gives a random element of A distributed according to that measure. So it's a bit like in probabilistic program. And E is just the center of mass. So it's pretty, I think it's almost better than usual partial evaluations.
It looks very nice. Thank you so much, Paolo. It looks great.
Thank you.
That was, really nice stuff. Thank you so much.
Thank you. Thank you for having me.
So if we have any questions or maybe asking for more information on references or whatever, can we